pick up a handful of sand at the beach, and what do you see?
I mean, you probably just see dirt, maybe some broken shells.
Right, exactly. A bit of sea glass if you're lucky. It's
I-
totally unremarkable. You just brush it off your hands and forget about it.
But if you take that exact same sand, right, and you melt it down, purify it, and slice it microscopically thin.
You are suddenly holding the invisible engine of the entire 21st century.
Yeah, it is wild to think about.
It really is. And welcome to this Special Science Thursday edition of our deep dive here on Topical Lens.
Because to understand how the global economy today rests entirely on, one single island in the Pacific.
Or how a graphics card company hit a $4.5 trillion valuation.
Right. You have to start with that purified sand.
Today, our mission is to decode the most critical resource on the planet, semiconductors.
We hear these buzzwords thrown around constantly in the news right now, like Nvidia, chips, Taiwan, AI.
Oh, constantly.
But if you stop the average person on the street and ask them to explain what any of that actually means.
Or how it all connects.
Exactly how it connects. You usually just get a blank stare. I mean, people know it's important, but they don't really know why.
And that is exactly what we are fixing for you today. We are going to strip away the jargon.
By the end of this deep dive, you are going to be equipped with the ultimate water cooler knowledge.
Yes. You will finally understand the invisible brains running the device you are listening to right now, and you'll be able to actually explain it to anyone.
So before we even get into the physics of what a chip actually is, we should probably look at the company that has become the absolute tabloid face of this industry.
Nvidia.
Right, Nvidia. If you follow the stock market or, really just glance at the headlines, Nvidia is currently sitting at a valuation of over $4.5 trillion.
Which makes it the most valuable company in the world.
Yeah. But to understand how they pull that off, we have to rewind to 1993. Nvidia was founded to make 3D graphics for PC games.
And then in 1999, they launched the world's first GPU, or graphics processing unit.
Which was great if you were a teenager wanting to play Quake or Doom in high resolution.
Right. But I've always wondered how a company making video game graphics became the king of artificial intelligence.
It really comes down to how a GPU actually works compared to a standard computer processor or CPU.
Okay, so think of a CPU like a genius mathematician. It can solve incredibly complex calculus problems, but...
It solves them one at a time.
Exactly. A GPU is totally different.
Yeah, it's more like 10,000 middle school math students.
I love that analogy.
Right. They aren't doing calculus, but they can solve 10,000 basic addition problems at the exact same time. We call that parallel processing.
So drawing a 3D explosion on a screen requires calculating the position of thousands of pixels simultaneously.
Exactly. That's parallel processing.
But here's where it gets really interesting. Nvidia's true secret weapon wasn't actually that hardware.
No, it was a software platform they released in 2006 called CUD.
That was the ultimate game changer. Up until 2006, a GPU was strictly for drawing pictures on a monitor.
Right. CUDA was a programming language that allowed developers to use those graphics processors for general everyday computing.
It basically turned this highly specialized gaming hardware into a universal playground for researchers.
They could use those 10,000 middle schoolers for anything they wanted.
Which created an enormous locket effect. An entire generation of engineers learned to code on Nvidia's platform.
So fast forward to 2012, when the artificial intelligence boom really kicks off with neural networks like AlexNet.
And AI, as it turns out, requires doing millions of simple calculations at the exact same time.
It needs those middle schoolers.
Yeah. Nvidia didn't just win because they had fast chips. They won because when the AI explosion happened, Nvidia's software was the only tool everyone already knew how to use.
It's one of the greatest platform monopolies in modern history. And that brings us back to the $4.5 trillion valuation.
Right. We do need to clear up a massive pop culture misconception here. That $4.5 trillion isn't cash sitting in a giant vault at Nvidia headquarters.
No, not at all. It's a temperature gauge.
It is the stock market's collective belief that AI is going to fundamentally change human society, and that Nvidia is basically the toll booth on that road.
Though, to be fair, their actual revenue is still mind-blowing. They reported around $216 billion in revenue for fiscal year 2026.
And data centers make up over 90% of that now. Video games are barely a footnote for them anymore.
Here is the most crucial detail, though, and probably the biggest misconception of all.
Okay, lay it on us.
Nvidia is what the industry calls a fabless company.
Meaning, they design the chips, they architect the blueprints.
but they do not actually manufacture a single one of them.
Okay, let's unpack this. It's like you're building a house, and suddenly the company that sold you the windows now owns the entire neighborhood and the roads leading to it.
Basically, yeah. They dictate everything.
But if Nvidia is just drawing up the blueprints and not actually building the physical chips, what exactly are they designing? What is a semiconductor at its most basic physical core?
To answer that, we have to strip away all the trillions of dollars and just look at the raw physics.
Okay.
A semiconductor is, fundamentally, a material that sits right in the middle between a conductor and an insulator.
Right, so a conductor is something like copper wire. It lets electricity flow freely.
Yeah, and an insulator is something like glass or rubber, which blocks electricity entirely.
That's the foundation. In physics, materials have something called a band gap.
Right. In a solid metal like copper, there is no gap. Electrons just flow. In glass, the gap is massive, so electrons can't cross it.
But in a semiconductor, like silicon, which happens to be the second most abundant element in the Earth's crust, by the way, the band gap is medium-sized.
So it's conditional. It conducts electricity, but only when we tell it to.
I like to think of it like a track and field hurdle.
Oh, that's a good visual.
Right. Conductors are a flat sprint. Anyone can run it. Insulators are a 10-foot brick wall. No one is getting over that.
Exactly.
But semiconductors are a 3-foot hurdle. If you give the electron just enough energy, maybe through a little heat, light, or an electric field, it can jump over that hurdle and keep running.
That is a perfect way to visualize it. We don't just rely on raw heat to make them conduct in computers, though. That would be chaotic.
Yeah, that sounds dangerous.
Instead, engineers use a highly precise process called doping.
So you're taking pure silicon and purposely contaminating it, right?
Essentially, yes. We introduce very specific impurities into the silicon to control how it behaves electrically.
Okay, so if we dope a section of silicon with an element like phosphorus, we are adding extra free electrons to the material.
We call this N-type for negative.
And if we dope a different section with something like boron, we actually create missing electrons, which we call holes.
Right, and this is P-type for positive.
And the magic happens when you sandwich them together. You put the N-type with extra electrons right next to the P-type with the holes, creating what's called a PN junction.
Which sounds technical, but it's really just the border between the two.
But how does that actually give us a switch?
Think about what happens at the exact border where those two materials touch. A few of the extra electrons from the N side rush across the border to fill the holes on the P side.
And when they do that, they create a neutral no man's land right down the middle.
Exactly. It acts like a dam. Normal electricity cannot flow across that dam. The switch is effectively off.
But because it's a semiconductor, we can change the rules.
Exactly. If we apply a tiny separate electrical voltage to that border, it gives the electrons just enough of a push to collapse that dam.
So suddenly, the entire material becomes a conductor, and the main current flows through.
And if you take that little voltage away, the dam instantly forms again, stopping the current.
That is brilliant. You've created a switch that controls electricity, but there are zero moving parts.
No physical levers, no mechanical clicking.
It's just manipulating the physics of dirt. That is the transistor.
Invented back in 1947 at Bell Labs by John Bardeen, Walter Brattain, and William Shockley.
That single invention is the foundation of all digital logic.
Literally everything. Every photo you take on your phone, every text you send, every AI prompt you write is just billions of these microscopic dams opening and closing in specific patterns.
So we have the science to make an electric switch out of purified sand. But here is the massive logistical leap. How do we get billions of them onto a piece of silicon the size of a postage stamp?
Because that is what Nvidia is actually blueprinting. A microscopic city of billions of switches.
Right. So how does that city get built?
Well, you are looking at the most complex manufacturing process in human history, without exaggeration.
Okay.
It starts with quartz sand, which is melted down and purified to an extreme degree. We are talking 99.9999999% purity.
Wow. Nines of purity. That's insane.
They grow that ultra-pure silicon into a giant, heavy crystal cylinder and then slice it into incredibly thin discs called wafers.
And those wafers are sent to factories called fabs to be processed?
Fabs, yes. Short for fabrication plants.
I was looking into the clean rooms inside these fabs, and it sounds like science fiction.
Oh, it really is.
They operate what's called a Class 1 clean room. That means the air inside is 10,000 times cleaner than a hospital operating room.
Because you are building structures at an atomic scale.
Right, so a single speck of dust falling on a wafer is like a meteor wiping out downtown Manhattan. It ruins the entire microscopic city.
And the crazy thing is the cleanliness is just the baseline requirement to even open the door.
Just table stakes.
Right. The real magic step in the fab is a process called photolithography.
Essentially printing the intricate circuits onto the silicon wafer using light.
Exactly.
Yeah.
And to talk about this, we have to introduce a Dutch company called ASML.
Ah, ASML. Quite possibly the most important company most people have never heard of.
Definitely. They hold a complete, impenetrable global monopoly on the machines that do the most advanced form of this printing.
Known as extreme ultraviolet lithography, or EUV.
These machines are the size of a public bus. They cost anywhere from $200 million to $400 million for a single unit.
And it takes multiple Boeing 747s just to ship one to a factory.
Yes. And the light they use is, well, extreme. It has a wavelength of just 13.5 nanometers.
That light is so delicate that it gets absorbed by regular air. So this entire printing process has to happen inside a total vacuum.
Right.
But wait, let me push back on this for a second.
Sure.
If this is fundamentally just purifying sand and then shining a really precise light through a stencil to print a blueprint, why can't massive wealthy economies like the US or China just reverse engineer the machines?
Just take one apart and copy it.
Yeah, why not just build their own factories tomorrow?
It is a logical question, but it completely underestimates the sheer mind-bending physics involved in generating that light.
Okay, how so?
You can't just look at an ASML machine and copy it. To generate that 13.5 nanometer light, the machine fires a high-powered laser at microscopic droplets of molten tin.
Wow.
But it has to hit those tin droplets exactly as they fall in a vacuum twice in a row to vaporize them into plasma.
Wait, it's shooting falling liquid metal in midair with a laser?
Yes, 50,000 times a second.
That is unbelievable.
And the mirrors used to collect and direct that flash of light are the flattest surfaces ever created by human beings.
How flat are we talking?
If you took one of those mirrors and scaled it up to the size of the entire Earth, the tallest mountain would be a fraction of a millimeter high.
Okay, yeah. You can't just steal the blueprints for that.
No, it represents decades of highly specialized incremental knowledge from thousands of suppliers. It is basically alien technology built by humans.
And because this process is unbelievably difficult, insanely expensive, and relies entirely on this one ASML monopoly, the world has effectively outsourced the physical baking of these chips to a tiny handful of players.
Which brings us to a terrifying geographic bottleneck.
Taiwan. Specifically, a company called TSMC, the Taiwan Semiconductor Manufacturing Company.
Remember how we established that Nvidia designs the chips but doesn't build them?
Yeah, the fabless model.
TSMC is the foundry that actually builds them. They produce roughly 90% of the world's most advanced logic chips.
Those are the ones under 7 nanometers that power Apple iPhones, Nvidia AI servers, and AMD processors.
The geopolitical reality of this is staggering. And just to be completely clear here, neutrally speaking, looking purely at the strategic facts without taking any side.
Right, we're just reporting the reality on the ground.
Exactly. This dynamic has created what analysts call Taiwan's silicon shield.
Because the United States, China, Europe, and basically the rest of the modernized world are entirely dependent on TSMC to keep their economies running.
Taiwan has become arguably the most critical geopolitical choke point on Earth.
The U.S. relies on Taiwan for its tech industry and advanced defense systems, so it's deeply invested in maintaining the status quo.
Meanwhile, China views Taiwan as its territory and heavily subsidizes its own domestic chip industry to try and overcome U.S.-led export restrictions on this advanced tech.
It is a high-wire balancing act. To counter this extreme reliance on one single island, the U.S. passed the CHPS Act.
Right, pouring billions into trying to reshore production, convincing companies to build these massive fabs in places like Arizona or Ohio.
And Europe is trying to do the same thing. But moving a supply chain this deeply entrenched and complex is like trying to move a mountain with a spoon.
If you want to grasp just how fragile this global supply chain actually is and how it impacts your everyday life, look at the car crisis during the pandemic from 2020 to 2022.
Oh, that is the perfect practical example.
When the pandemic hit and lockdown started, automakers panicked. They assumed nobody was going to buy cars, so they canceled their massive orders for chips.
But at the exact same time, demand for laptops, webcams, and gaming consoles absolutely surged because everyone was stuck at home.
So TSMC and the other foundries naturally shifted their production lines to make chips for consumer electronics.
But then car sales bounced back way faster than anyone predicted. The automakers went back to the foundries and said, hey, we need our chips back.
But the foundries had already moved on. And here's a crucial point that clears up another misconception. Not all chips are the same.
Right. Cars generally do not use the ultra-advanced cutting-edge chips that Nvidia designs.
No, they use older, thicker, highly robust legacy chips because a car's computer has to survive extreme heat, cold, and constant vibration.
A modern car has anywhere from 1,000 to 5,000 of these legacy chips running everything from the engine timing to the anti-lock brakes.
And because automakers use just-in-time manufacturing to save money, they hold almost zero backup inventory.
So you had a situation where millions of brand new cars literally could not be finished and sold because they were missing a $2 chip that controlled a windshield wiper or a window switch.
It is wild to think that your ability to buy a car in London or Los Angeles was entirely dictated by whether a factory in Taiwan decided to print a chip for a laptop camera instead of a brake sensor.
It showed the entire world that chips are the new oil.
But unlike oil, which you just pump out of the ground, chips require the most advanced intellectual property on the planet.
And right now, geopolitics and economics are on a collision course with an even bigger, more fundamental obstacle.
The literal laws of physics.
This is where the story gets really sci-fi. We have all heard of Moore's Law, right?
Yeah.
Gordon Moore, one of the founders of Intel, predicted back in 1965 that the number of transistors you could fit on a chip would double roughly every 2 years.
And for decades, that held true. We just kept making the switches smaller and smaller, packing more of them onto the silicon.
We did. But we need to shatter a major pop culture myth right now. When you go to the store and buy a new phone, and the marketing material proudly states it has a 3-nanometer or 2-nanometer chip.
Yeah, that is purely marketing.
The physical transistors are not actually 2 nanometers wide anymore.
Right, because if they were actually 2 nanometers, we would be dealing with individual atoms. A single human hair is about 80,000 nanometers thick.
So what does 3-nanometer actually mean?
Since about 2012, those node names lost their physical meaning. It is just an industry label to describe the density of the transistors, how closely packed they are.
Okay, got it.
But even so, the features we are building are getting incredibly small, down to parts that are just a few dozen atoms wide. And when you get down to the atomic scale, the universe stops playing by the normal rules of classical physics.
We hit a wall called quantum tunneling.
Yes.
In the classical physics we use every day, a transistor is a solid switch. When the dam is closed, the electrons are blocked and no current flows.
But at the quantum scale, particles don't act like solid objects. They act like waves of probability.
So when the barrier in our tiny transistor gets too thin, the electrons just teleport right through it. They leak across the barrier even when the switch is explicitly turned off.
Imagine turning off your kitchen faucet, but the water just goes straight through the metal valve and keeps pouring into the sink.
That is what electrons do at this scale.
Exactly. It defeats the entire purpose of having a switch. It causes massive heat generation and drains power incredibly fast.
So if 3 nanometers is just a marketing term and we're practically playing with individual atoms that are teleporting through walls, are we actually at the end of Moore's Law? Have we finally squeezed all the juice out of a grain of sand?
It is the biggest debate in the industry right now. We haven't necessarily hit the absolute end, but we cannot just shrink things the old, flat way anymore.
Engineers have to be infinitely more creative.
Because we can't easily build flatter and smaller, we are building upwards.
If you can't build wider out into the suburbs, you build a skyscraper. But how does that stop the electrons from leaking?
Think of the transistor like a leaky pipe. If water is leaking out, putting a flat patch on top isn't enough. You have to wrap your hand completely around the pipe to clamp it down and stop the leak.
So we moved from flat transistors to 3D designs called FinFET.
Right, and now we're moving to gate-all-around architectures where the control gate completely surrounds the silicon channel on all sides to physically trap the electrons and stop that quantum leakage.
We're also changing how we build the overall chips. Instead of trying to print one massive, flawless chip, which is incredibly difficult and yields a lot of duds.
Companies like Apple and AMD are using chiplets.
They print smaller individual modules and stitch them tightly together like a patchwork quilt to make one big processor.
We are even looking beyond silicon entirely. for certain applications.
Silicon has been king for 70 years, but for specific extreme uses, we are moving to new materials.
Gallium nitride and silicon carbide are becoming huge, especially in electric vehicles and heavy power grids, because they can handle much higher voltages and extreme heat without losing efficiency.
So the innovation isn't stopping, it's just pivoting.
Exactly.
We are literally engineering our way out of the physics corner because the demand for computing power driven by this AI revolution that Nvidia sparked is completely insatiable.
The industry has no choice but to keep pushing the boundaries.
Okay, let's take a breath and recap this incredible journey for you. We started with ordinary quartz sand, purified to an absurd degree and sliced into wafers.
We learned that semiconductors are carefully controlled electrical switches with no moving parts, relying on a band gap to let electrons flow only when we want them to.
Nvidia, the $4.5 trillion giant, doesn't actually build these chips. They use software moats like CUDA to architect the brilliant blueprints.
ASML in the Netherlands provides the magical vacuum-sealed machines that print these blueprints using extreme ultraviolet light and vaporized tin.
And TSMC in Taiwan is the irreplaceable foundry that actually turns those blueprints into the physical chips powering our modern world.
It is a miraculous, interconnected, and highly fragile global ballet.
It really is. But before we wrap up, we want to leave you with one final, slightly mind-bending thought to mull over.
Okay.
We have spent this entire deep dive talking about classical computers moving physical electrons to represent binary ones and zeros. It is the foundation of everything humanity has built in the modern era. But what happens when we throw that entire rule book in the trash?
You're pointing toward quantum computers.
Yes. If traditional semiconductors are hitting the physical limits of moving electrons, quantum computing is the wild frontier.
Instead of a transistor being strictly a 1 or a 0, quantum computers use qubits.
Thanks to quantum superposition, a qubit can exist as both 0 and 1 at the exact same time.
It's a completely different paradigm. A quantum computer wouldn't just be a slightly faster laptop.
No, it could solve specific, incredibly complex problems in a few seconds that would take a classical supercomputer 10,000 years to crack.
Things like simulating molecules for completely new medicines or breaking modern encryption instantly.
So imagine what happens to the global balance of power. What happens to the geopolitical choke point of Taiwan, to the ASML monopoly, and to trillion-dollar empires like Nvidia when the silicon era eventually gives way to the quantum era?
The game won't just change. The entire board will be flipped over.
Exactly. Next time you brush a grain of sand off your hand, just think about the $4.5 trillion empires built on top of it and what unimaginable tech might eventually replace it. Thank you so much for joining us for this Science Thursday deep dive on Topical Lens. Stay curious.